right. Share my screen. Here we are. You all see this?
All good.
All right. Fantastic. I'll get started. So welcome to the last class on galaxy morphology. And today I wanted to talk a little bit about future science and machine learning. Machine learning is a part of, well, statistics / computer science that is worth its own lecture series, and I am not the person to give it. But this is where we're moving with galaxy morphology in the very near future. So let's see, about 20 years ago, some of these first algorithms came out, and I remember a kind of like a crop of papers appearing like, oh my gosh, we can classify galaxies this way. While that was true, that was sort of help for that particular survey. So they managed to do pretty okay with the very first Sloan data releases, for example. And then there was no big data sample to follow up. But as we're looking at the future, we're looking at many more deep surveys with both ground-based and space-based telescopes. So we're sort of expecting way more data than we can deal with. And this is where machine learning is sort of inevitable. So this is lecture 7, and the future for this is with the motivation that I was talking about. We have the Vera Rubin Observatory. This is a large 8-meter class telescope now being commissioned in Chile. You kind of see the building there. It's actually progressed quite a bit further than that. And so that will take a 5-colored image of the entire sky every week. So not only do you have in the end, you'll end up with a very deep image. So that will tell you a lot about galaxy morphology, lots of low surface brightness structures, all those things. But also you have time series. So suddenly you have to sort through all this imaging data, and it refreshes every week or so. So you have to start identifying what things are based on their variability. At the same time, in space, the Euclid Space Telescope effectively will image the entire sky in the near infrared, but now to a resolution that's very compatible with Hubble. And so that is a high level of detail for literally millions of galaxies. So if you want to start classifying them, doing that by eye or even doing that with crowd science becomes very, very challenging. And the Roman Space Telescope, very similar to Hubble, 8 filters, very deep surveys, maybe not the entire sky like Euclid, but still millions of galaxies, easily millions of galaxies with spatial information. So now you have to classify these things. You have to group them together, and for that you need machine learning, pretty much. But that's not the only thing. So I just wanted to do one thing here. Now that we have, we're getting consistently multi-wavelength data on all the galaxies that we're looking at. So this is from Boris Hausler's latest paper. What I think is useful to also point out is that rather than doing individual Searsic fits on each filter and then sort of combining the catalogs later, you actually combine the information across multiple wavelengths. You say, well, there has to be a gradual change in effective radius and a gradual change in Searsic index. So you sort of use all the information at your disposal when you're doing your Searsic fits. When you're doing your total morphology classification. So you're folding everything in and combining. So the idea here is that if one filter suddenly is very different from the trend that you see from all the other filters, that means that fit has probably failed and you should redo it, or you should, it gives you a prior for the fit as well. So not just the machine learning, but also the classical analysis using Sursic indices, for example, or morphometrics or anything like that is going to benefit from the fact that you now have deep data across different filters and different wavelengths. So I think we're going in a more classical analysis. We're going for more holistic approaches, and at the same time, we're going for this machine learning approach. So why do we use machine learning, right? So cute little robot. That's always the robots are always inevitably very cute when you're looking at machine learning talks. First, you can recognize things, right? So you can sort of group things together and you can label like cat, dog, cat, dog, cat, dog, right? This is
Okay.
the other one is that you can predict missing data, right? So that's, you can say, you can make a prediction, you can fit a trend and say, this is the prediction. The other one is that you can simply group together based on similarities and then classify afterwards. And the last one is that you can simplify that. So you can find like this is the common, prediction. I'm seeing a chat.
I still just see your title slide.
Oh,
It hasn't moved.
oh, that's annoying. Play. Can you see it now?
I see title.
Nothing else.
Nothing else.
Oh. Okay. Stop the share. Share screen. I'm just going to do the whole desktop. Can you see the desktop now? Does it change now?
There we go.
Okay, fantastic. Okay, so I was talking about these three new telescopes. Oops. These three new telescopes that are going to revolutionize our imaging, our morphology classifications, basically ordering. We now have of order 250,000 in slow resolve. So maybe all told, we're sort of at the million level, and all of these, each individual survey will already do several million. So we're upping everything by an order of magnitude. And in order to do that, that means that all your existing ways to do analyses. So this is sort of an existing way to do analysis, right? You can do a Sursic fit, but you can also do a Sursic fit across filters and say, hey, well, the galaxy doesn't dramatically change Sursic indices from one filter to adjacent filters, so there has to be like a smooth transition, and so that's what this new way of doing Sursic fits is. So that's a classical way, but you can sort of only do that on a few thousand galaxies, 10,000 of galaxies, maybe the Sloan Digital Sky Survey in a little bit of time. But if you want to go to the next step, if you go from 1 million galaxies to 10 million galaxies or 100 million galaxies, that order of magnitude jump sort of breaks your current analysis pattern. You simply can't do that in reasonable amounts of time with a reasonable computing power. And so, or you can't reasonably do that, a galaxy zoo on millions of galaxies without involving the entire planet, for example. So if you start running into like physical limitations of existing analysis techniques, then it becomes that's sort of the breaking point where people start talking about big data. Big data is our old analysis broke and we can't do it anymore. So why do we use machine learning? I already talked about this. We can either recognize things, so actually group things in known classes. We can simply group things and classify later. So like, these are all similar, these are all similar, these are all similar, look at them. And it's like, here's a typical example from them. You can make a prediction, meaning that you have an image, for example, and go, well, there has to, and that's a face, there has to be eyes in there. Or you can simplify, you can say you can get the general shape from all the images, like cat shape, that has to be a cat shape in there. So machine learning comes in these three components. First, we have features, so input. So that could be images of all the galaxies that we have just observed. It can be morphometrics, for example. Those are fairly straightforward to compute. So maybe we've got we've already generated those from all the images we're getting from the Vera Rubin Observatory, for example. Or we did Sirsik fits, again, automatic, everything is pipelined. Or we do a photometric measurement, so we have colors, for example. So all these things are, you either have a feature space that is the actual images, or you have a feature space that's made out of images and like additional data, or it's the catalog data. And so that's the space that we're trying to classify in. So we hope that has the resolution to actually tell things apart. And then in the middle is the machine learning algorithm, which is basically a black box to most people. What it essentially is it can classify based on the feature space, and it can either label things, cat, dog, cat, dog, cat, dog, or it can go, it can predict a measurement. So it goes, all the features go in and it says, oh, this is, small cat, the size of the animal. So basically this animal is 30 inches long, that kind of thing. That has a sliding scale, so that's a measurement. So you can either classify or use regression. But if you want to classify, you need to have labels already. So the labels, so you need to train the machine learning, like it has to learn how to do that. So you need to have both the feature space and labels or the measurements already ready. And so for that, we often use Galaxy Zoo. The input is going to be on the left. The output is what we're after. And sort of the machine learning is the means to an end. It is not the end goal here to optimize that. To optimize that, we only do that so that we have clean classifications, for example. The machine learning thing is a very broad set of algorithms, and I'm not going to overview them, but it sort of splits into supervised and unsupervised learning. The supervised, it means there is a training set, so we already know what we're after. We want to classify this according to the Hubble tuning fork, for example. We want to classify this according to the Galaxy Zoo questionnaire set, right? We have a set of classes that we want we think everything fits in, and that's what we want everything classified as. And we have a training set, meaning that we have done this already on a subset of the data, and now we want to train an algorithm to basically emulate our classification as best as possible, and then release it onto the rest of the catalog. Unsupervised means you don't have a classification training set. Like you don't know what, how many ellipticals, or you don't have a list of these are all elliptical galaxies, these are all disk galaxies, these are barred galaxies. You don't have that yet. You just go, here's all the images, group them together into similar looking things. The problem is that then, of course, you have to say, how many different groupings do you want? Is it A and B, or is it A to Z, right? So that's a big difference for the algorithm. The algorithm doesn't care or should even know how many classes there are. So, but it does run on the whole data set. And so you'll end up basically with little piles of, here's a bunch of things that look the same. Here's a bunch of things that look the same. Here's a bunch of things that look the same, according to my feature space. Again, if the feature space doesn't have the resolving power to separate things out, it'll just all end up in one pile. So the other fun thing when I do a class on machine learning is always like, is it regression or is it classification? So we tend to think in classification because we have classes already, right? So this is, we've been working with Hubble's tuning fork for the last 100 years. We've been using early versus late type, which, as much as I despise that particular phrasing, we do have like, it's either here or there. The number of type 1, type 2 kind of classifications in astronomy, and especially morphology, is abundant. So we have discrete classes. It's either this or that. It's either this, 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 or this, right? So those are classifications. That's the kind of thing that's where, supervised machine learning algorithms are perfect for, because you already know the classes. You don't expect new ones. This is what they are. Fit them all in these, please. The regression predicts really a value based on the features. So it can say, here's the image, this is its stellar mass. Now it'd be amazing if you just can feed images to a machine learning algorithm and get something that we can otherwise only get from spectra, for example. Spectra are more expensive than images. Images are easier to get with a telescope. If you want to do a spectrum, you're basically smearing out the light. So the more you smear out the light, the longer you have to stare at each object. So spectra are always expensive, meaning that spectroscopic surveys always lag a little bit behind as in the number of objects that we can analyze compared to imaging data. With an 8-meter class telescope, I can get millions of galaxies, but only thousands of spectra, right? So that's sort of the trade-off. So what happens if I get images, maybe a color image, I get a color image and I can predict something that you otherwise only can get out of spectra, right? So that's another thing, like you can actually generate more information, you can actually squeeze out the last of the information from your imaging data. So feature space, the feature space can be anything, right? So it can be the morphometrics, for example. Morphometrics is my favorite kind of feature space because I sort of understand morphometrics the best, but it's literally anything that you've measured on the image. Or this, it can be, for instance, a Sersic fit, or multiple Sersic fits, or a combination of Sersic fits and morphometrics, or photometry, colors, Sersic fits. You have to figure out what kind of parameter space you want. They're picking these right features, and especially not picking the ones that don't know about certain morphology classifications. For example, if I pick the catalog entry number, this is entry number 412, that should not know anything about morphology. So that is just noise. And so you then having your algorithm work on complete noise on a random number. And so you want to maximize the information, so morphometrics that actually know about galaxy morphology, and minimize noise features. So this is called feature engineering, making sure you pick the right ones, don't add more, don't add ones that are that are basically measure the same thing, because then you're implicitly overemphasizing that one feature. So making sure that you get a nice orthogonal data space. So since you end up with a multidimensional feature space, so morphometrics, for example, concentration, asymmetry, smoothness, and then you have Genium 20, and then you have a Sersic index and a half-light radius, right? So that's 7 right there, and maybe you add a couple more, and so before you know it, you have 10 of these things that you have. You can see here. How do I visualize that a little better, right? How do I show that as like, how does my sample spread over these morphologies? And so I use often something called a self-organizing map that sort of boils down the 7 dimensions down to a single image. And so it groups similar ones together. And so if you have a lot of sources in your catalog that are have one particular set of features, they sort of all clump together in one set, and they're not in another. And so you can see that on the left here, that's the weight maps. And then you can see with the labels, you have features on one side, and then you have the labels. So it's like, oh, the number of spiral arms, for example, like Galaxy Zoo has identified how many spiral arms this has. And so you can see where, 1 spiral arm labels and 2 spiral arm labels, et cetera, end up. And you can see if they actually separate out at all. And so you can have a first pass very quickly to see if the things actually separate out, or if they're all kind of spread out. And it's like your feature space is not very good at separating different classes out. So an example of this is what I've been working on the Hydrec cluster. So this is these are H1 measurements done by the Wallaby survey, and so you have much improved H1 mapping. So that you suddenly have resolved galaxy gas images. And so there's an opportunity to see if we can, we have a morphometric space. So we have our feature space, and then we also have labels. So the other part was that we needed labels if you want to classify it into A or B. And the A, B here is these galaxies are either undergoing round pressure stripping from the intergalactic medium, or they're not. And so we have the classifications, and this is the best way to do it, because if you do this and somebody else has done the classifications, so these are sort of like you open the envelope and say, okay, these things are RAM pressure stripping, these are not RAM pressure stripping, and so you compare that to the morphometric. So you have this morphometric space, and you see where your two classes lie. You typically make these like triangular plots where you plot everything against everything else, and you see like do the different kinds of classifications actually separate out, and the answer here is like barely. And so this is the kind of thing where a simple line cut won't do. So that's exactly where machine learning might actually improve things, where you say, okay, I can't do a simple cut classification. Can I do something a little more complicated? Can I optimize in some way? This is a different set of the classifications. Not all of them work. And so can I keep cutting, for example? And this is called the decision tree. So if you start with machine learning, decision trees are the best place to start because it's conceptually the easiest thing to understand. Basically, instead of going with a single cut, you go, well, if I split it down the middle here along this parameter, I get most of them over here and most of the other kind over here. And then I can split and split and split and split until I basically end up with two, I say the word basically too much, sorry. I end up with all of one kind in one cell and all of the other kind in the other cell. So you end up with clean samples that way. You can pare down the number of features. Again, that's feature engineering. So you can go like, well, here I'm seeing that most of the splits are happening using these features. I've used all of them here, but not all of them get used to classify. So if I just use Gini and the half-life radius, for example, oh, actually that works just fine. So it's an iterative process where you have your features, you try it out, you see how good the classification works. For example, on like a little test sample that you left out of the training, and see if that classifies as well. And you go like, and then you realize that, oh, these features can be dropped, and you actually simplify as you iterate out. You can do this particular loop until, well, ever really. So it's important to remember that it will never be perfect. And so you should probably at the beginning say, what's good enough? What's the contamination level that I can live with? If I want to learn about elliptical galaxies, and well, if I've got 10% contamination by S zeros or something similar, SAs, I won't complain. So 10% contamination is something I can live with, right? So that's an important decision to make, preferably before you get started with all the machine learning algorithms. The data can, however, can also be the images themselves. And so what happens here, and this is the thing that sort of pushed machine learning to the forefront of, I think, the public consciousness, really, because suddenly things like Facebook and Google could identify us, right? They could find our face in whatever image and basically say, hey, is this you in your friend's picture? That kind of thing. The social media stuff because it kind of got creepy very quickly. But the reason that happened is because you have images, and the images sort of look the same. I mean, it's all people with noses and eyes and stuff. And so you have a set of the feature maps basically are things like edge detections and circle detections and other algorithms that basically turn the image into a set of features that then get subsampled. They're all a bunch the same, and so you average out, and so that reduces the amount of data, and then you convolve it again and subsample again. So there's some combination between convolving the image, so that could be smoothing, but that can also be edge detection, that can be other ones, and subsampling sort of turns the whole thing into just a single set of nodes, it's called, and the output can be, this is you, or it isn't you, or this is you, your friend, your cat, your bartender. All these things are the output can simply be labels, and the labels are fairly straightforward you or not you, right? So that's a quick labeling effect. So the reason that we got onto that is because it became clear that we can find the eigenvalues of this parameter space. So you start with images. Again, you start with the images, the data, and you find the principal components of those. And so that's, I love the fact that they use the word eigengalaxies, kind of like eigenvalues for eigenvectors in orthogonalizing a parameter space. And so what you see on the right here are the principal components. So you have a component that is just a central pixel, but then you have ones that are the rings around it, or like half. You know, the at the bottom you see like this side is dark and that side is light, and the other one it's like it's flipped. And so you combine these in certain levels, and you end up with you can describe any one of the galaxies in your survey. And the levels that you need, the strength of the different eigenvalues, the eigengalaxies, means that you have, if you combine this one and this one, you end up with an edge-on galaxy. If you combine those two, and those two are strong, then you end up with like a very compact elliptical. So having this like set of eigenvalues to describe all the galaxy images means that you can say, here in this parameter space of eigenvalues, this is where ellipticals live. That's where edge-on galaxies live. That's where face-on spirals live. So you can, within a galaxy, you can actually separate the components very quickly. And so this is called principal component analysis. And it's often the first thing you do. You can see how many independent components you really have in your feature space. And in this case, it's a fair number. It's 12. So that's a lot. Often you end up with only like 5 or so, or less. So you can all do, I mentioned the morphometrics already. So what you end up doing is like, that can be your feature space as well. But you have your training set for the visual classifications, and then you can ask a simple classification question. Is it merging or not, right? So you start with the question, like all science questions, you start with this is what I want to know. This is what I need to know. This is what I need my machine learning for. Because if you sort of go on a fishing trip going like, I wonder if there's something interesting in this sample, that's not clear enough, and you can't classify based on that. But using the images as features, you can do quite a bit. And so, for example, here's an example from a paper that took the images and then as the radial profiles, not the Searsic fit, but the radial profiles that went with those images were the output. Now that's already a data reduction, right? So you don't have the full image anymore, but you just have the radial profile. But they use the images, to train a convolutional neural network to predict the profile. So then you can just feed it the rest of the survey's images, and out come the radial profiles. So you can sidestep the Searsic fit or the isothermal fit altogether, and just end up with color profiles of these galaxies immediately. That's pretty amazing, right? So that can be faster than Searsic fits. That can be just as reliable as for Searsic fits, and you can just run through images very, very quickly. You can predict morphometrics, for example. So you take the images and you have a label. The label here is the morphometric value, the concentration, the asymmetry, right? And so you have, here's the image, this is the asymmetry I measured. And now you have a bunch of new images with similar characteristics, similar filters, similar telescope, but now it's just producing predicted concentration and asymmetry. So you can have it, as long as you know what you want, machine learning can get it to you fairly quickly. But the main thing that we use are convolutional neural networks for this use on images. So you have these filter kernels, they're as big as the actual images, and then we subsample in order to, not do as many computations. So you subsample filter, subsample filter. There's sort of like a combination that you prefer, but at the end, it either produces a label or it produces a value. And so the convolution, at the beginning, you have to do it the least. So often as not, we actually end up the Google initial convolution. So those layers, Google just has made available to everybody. So we're using this initial convolution that is trained on people's Snapchat, right? So it's oh no, that's video. So on Instagram, right? So on all the pictures that everybody has ever uploaded, and so they're mostly of cats. And so this is all those first convolution layers are simply the same. The medium rate where we step down and also keep convolving, that's the kind of part that you really train for your specific classification. For example, you can take the images from Sloan and turn them into a metallicity. And so the metallicity being here, of course, astronomers saying that everything that isn't hydrogen or helium is metal. And so most of it is measured using an iron line. So really, we're talking iron levels. But sometimes we use oxygen. So it's oxygen or iron levels in each galaxy. So we have an image, and the label, the thing that we're trying to predict is metallicity. So it's a value between 7 and 12, and that's the prediction. So it's a regression problem, right? So it's a range of value. It doesn't have two clear classifications. So we take the images, it steps down, there's features, it steps down, features, and then it predicts a metallicity at the end. And so that works remarkably well. It works better than it should. So you can see at the bottom there, like the true metallicity, which we got from spectroscopy, and the predicted metallicity are good within a tenth. This is a logarithmic scale, so within a tenth is within a factor 2 and even less. So that's actually pretty accurate for something where you start with an image and end up with something that you otherwise only can measure from metallicity, from spectroscopy. So if you supposedly have like way more images than you have spectroscopy, basically the way extragalactic astronomy is always going to be, then you can start predicting metallicity for all your images. So that's exciting because you can say, hey, look, here's all the metallicity values that we predict. And anytime you find something that is massively different, that will be interesting. That is worth following up further. So another example of that is so predicting the spectra from these of galaxies based on just the images. And I thought this is a fantastic example. This is, of course, my favorite galaxy, and I get to talk about my favorite galaxy because this is my class. UGC 2885, or better known as Rubin's galaxy. And what I was wondering about was whether or not the central galaxy had an AGN, an active galactic nucleus. Now that shows up as a couple of really bright emission lines and a specific ratio of those emission lines because AGNs have a very steep, very steep spectrum. So it pumps out the immediate disk around the supermassive black hole pumps out a lot of X-ray and gamma ray and ultraviolet photons. So the gas around it is very highly ionized, and as a result, you get these different emission line ratios than you get, for example, near a young bright O star. So there's a clear difference in spectral fingerprint. Of course, I went into the Sloan Digital Sky Survey because often, if it's a bright galaxy in the northern hemisphere, surely that has to be in Sloan, but it wasn't. As you can see here, Sloan ended just short of Rubin's galaxy. So I needed to go get a spectrum. From broad colors, I couldn't tell anything. So this is this is all the classical analysis components, right? You go in, you find the spectrum, no spectrum, all right, fine. Are there broad infrared colors? Infrared colors also tell us whether or not it's an AGN. Yeah, it's sort of below that level, so maybe not. And so here's a machine learning application that actually could answer this. So there are two things that happened. One was they took all the SDSS spectra and turned them into eigencomponents, so to speak, so eigenvalues. So with just 6 values, you basically reproduce all the broad shape of the spectra, including the absorption features, including the emission lines. So it's actually compresses the spectra quite a bit. And then with a hybrid neural network, again, input images, convolving and stepping it down, will actually predict the eigenvalues that the VA encoder came up with. So you can actually say, here's the image. This is the eigenvalues for this galaxy's spectrum, and that will produce a spectrum. So you can predict spectra based on images, which is pretty darn cool. Like not just the metallicity, but the whole spectrum. And so through this sidestep of the eigenvalues. As you can see, this works pretty well. Like the actual spectrum and the predicted spectrum are red and black, and you can barely see the black. So the prediction is very, very solid. And for this particular galaxy, we got the top line. So it's sort of in between a star-forming galaxy, which is the blue one at the bottom, and an AGN, which is at the top. So we are curious what happens. And so I went rooting around for spectra. And so I found spectra, collaborators found spectra in their paper archives, thanks Bill Keel, and there was also ones that we actually took one with a multi-mirror telescope. So a bunch of these spectra were taken for the nuclear region for Rubin's galaxy, and as you can see, the black one is the prediction from the machine learning, and all the colored lines are, so the orange one and the green one are archival data. The blue one here was one that came out of a different instrument, and then the MMT was actually dedicated observation for that, and all of them seem to agree with what the machine learning prediction was. So you can predict using images what the and so that's a VAE, the principal components basically of that spectrum are. And as you can see here, most of the training set lay in a different part of parameter space where this galaxy was. That's pretty neat, because that means even on the outskirts, even where you don't have all the training available, you can still make a good prediction. Even BPT diagrams seem to agree that's another analysis on AGN. So this is sort of like a success story of machine learning. Of course, we did do this rather carefully, but you can have machine learning predict metallicity, spectra, other galaxy quantities, and then follow it up. For example, you can weed through your sample and go, these are the ones that should be interesting. And that will help you. So that helps with not using labels or not having to use labels. The labels typically come from morphology from Galaxy Zoo. So this is the kind of questions that you get. And so you can either say this is, so is it a edge on disk? Yes, no, right? So the yes, no questions are the most useful. Or is it something like how round is it? Or how, like, so then it's you switch from things that are classifications to things that are more regression, meaning that you say, okay, is there a range of values? Is there a range of voting patterns? For example, if you start, instead of saying this is a disk galaxy, yes, no, that means you put a cut into, if more than half the people say it's a disk galaxy, it's a disk galaxy. So you already put a choice in there. And if you don't want to do that, you actually have the machine learning algorithm predict the voting fraction. So at that point, you basically simulated the entire Galaxy Zoo crowd in your machine. And so you can have it classify new galaxies, provided the data that you show it are the same as the data that the Galaxy Zoo worked on. And so you can do things like help have machines help a Galaxy Zoo classification effort. Because, well, there's a few things. Machine learning is fantastic, and Galaxy Zoo is fantastic, but they do have some weaknesses. In the case of citizen science of the Galaxy Zoo, people get sick of the same looking blobby things over and over again. So if you have things that all look the same, and you're already getting like a few classifications on that same blobby thing, and it says, oh yeah, all these are ellipticals, and everybody agrees that they're ellipticals, you can retire those objects much faster, because the machine learning algorithm that runs in the background starts going, oh, those are all similar. Oh, they're all this label. Okay, cool. All these things are this label, and I can retire these objects, and we can just focus on the new ones. And so the process of so you can do the whole Galaxy Zoo thing. This is what's called Galaxy Zoo Express. So Beckett all 2018 simulated a algorithm that would have assisted the original Galaxy Zoo. And this is the kind of thing that we can start thinking about doing with LSST, for example, or the Euclid. So that will be very interesting to see if machine assisted citizen science, a hybrid approach, will actually help here. I keep thinking of that as the way my photo album, as soon as I clicked, yes, that's my little kid. It's after you've done that for 3 pictures of that day, it sort of goes, oh, that little pink blob in the rest of those pictures in that day are also your kid. So it also, so it sort of groups those together. You only have to do it 3 times. You don't have to do all 800 pictures you took that day of your kid. It sort of collapses that and goes, oh, they're all the same. Got it. So that works. But we still are left with some interesting problems, one of them being transfer learning. If you trained your algorithm to perfection on the Galaxy Zoo that was done on the Sloan Digital Sky Survey, which we see on the left here, and you go from that data set to, say, the Vera Rubin Observatory, which is a different telescope that observes deeper, that sees more detail. And so the features in the data set that you're going to apply this to are a little different from the ones that you trained it on. And they're not completely different, but they're different enough. So you may have to keep learning with the new data. For example, build a training set initially. You don't have to retrain completely, but you don't have to not retrain completely. Does this make sense? So you may have to add a few extra steps of training so that the algorithm, for example, has adapted to the new data set. So that's called transfer learning, and it's a tricky problem. But if we do this kind of thing where we move from Hubble pictures to Euclid pictures, or we move from SDSS to Vera Rubin, then yeah, we definitely want to be aware of transfer learning problems. So machine learning is the way of the future. This is how we're going to classify galaxies, and we're going to get additional values out of the images that we get, right? Not just are we be able to classify things along the Hubble sequence, not only can we find things that don't fit the Hubble sequence, but we will also, we very likely can get values or predictions for things that we otherwise needed additional time with a spectrograph. So we can really get the most out of our imaging data. The main reason that we're moving to this is because we cannot deal with the data flow unassisted anymore. This is not just a Rubin Observatory. This is not just Euclid. This is not a combination of those two. It's also things like the square kilometer array, new radio information, all that stuff is, you can't look at all your data anymore. So you need something new. Similarly, there's also way more contamination. We have to deal with a new kind of contamination. Satellites are not a rare event anymore. They're almost a guarantee, especially if all the constellations are up. So machine learning is definitely going to be a component of where you, for example, take out satellite trails. So you either classify in known classes. So if you only want the known classes, you use supervised learning, or you use a posteriori classification, and that's unsupervised. The unsupervised means, however, the plus is that you can have, oh, there was this class of galaxies I didn't know about and didn't exist in my original set of classes, in my original Hubble sequence for tuning fork, for example. And so if you expect the unexpected, if you expect new classes, or at least want to allow for new classes, you probably use unsupervised machine learning. However, if you go, I just want to classify everything into spheroids and disks, and I'm pretty sure everything is a spheroid or a disk, then you'd use supervised machine learning. going from the training to the science data, or from like one survey to another, the transfer learning can be tricky, and it is something that will show up because the feature space is slightly different. So as always, with anything that is computer sciencey, garbage in means garbage out. So if your features cannot distinguish between disks and spheroids, don't expect machine learning to magically do it for you. This is not a magic black box. It is simply a fitting routine or a classification routine that emulates the properties of your data, your training data, as best as it can. So it's always good to see how you do and see why it does the thing it does. So see if you drop a feature, if suddenly it performs equally well, then that feature wasn't doing anything. Okay, so that gets me to 45 minutes. Fantastic. Are there any questions about morphology and galaxy morphology and machine learning?
I do have a question. Thank you for the classes this summer. That was super interesting, and I might be biased because I like this area anyway. But I was going to ask, as far as morphology overall, where, I guess, current and I guess near future, where do you see like still unresolved questions or issues just in the field of morphology?
So low surface brightness is where we're going to get a lot of new information. And so I talked about that 2 weeks ago. So that's where you see those streams. Those streams are hard to find, but suddenly we'll have, for instance, with Rubin, the Rubin telescope will have that information for most nearby galaxies in the southern hemisphere. And so we finding those things, reliably classifying them, because that doesn't fit on our Hubble tuning fork, right? How many of them have loops? How many of them have these umbrella-like plumes, for example? And so I can see something where machine learning and the low surface brightness universe kind of mesh. Another one is basically separating sources into individual components. So that is true for the galaxies, the fields themselves. So because the depth is going to go up by a couple order of magnitudes, there's going to be barely any space on an image that is just background. It's all going to be part of some object or another. And so disentangling what belongs to where and actually separating everything out, that's actually going to be really tricky. That's a technical challenge that I think we haven't quite solved yet, but that should be it's going to be a different way of doing than we've been doing so far. Every time we look at a Hubble Deep Field or anything like that, we sort of see all the little galaxies, but like a sea of black in between. That sea of black is going to disappear. They're all going to blend together because we can now see, we grow each object until the low surface brightness, so they all sort of flow together. And so how do we separate all that out? The new things, the things that I think are going to be very interesting is to see, we're going to see the very first galaxies. James Webb has more than even odds to see the redshift 15 galaxy that is the very first, made out of the very first stars. And very likely we'll see the redshift, 12 galaxies that appeared right after the first stars. So we'll definitely get an indication of how big galaxies were right when they got started and how that evolved over time. What I think, and I haven't talked about this here, but we have kinematic information as well on galaxies now and stellar populations. So we can actually separate out how old the bulge is, how it's moving, and not just, in one image see that it has this profile, but you can see that it has this, like this age of stars, and the disk is, these 3 ages of stars. And so you can actually, this is called galaxy archaeology. We talked about it in the low surface brightness sense, but also that dovetails with getting spectroscopic information on nearby galaxies, so we can actually pick apart when they happened. So I think that those two, like we will maximize our look back time, and we'll pick apart the nearby galaxies to a much greater degree. I think those two will tell us what has been happening to galaxies over time. I think that's it's going to be a combination of the two. So that's where galaxy morphology, I think, is going to shine, where you can actually tell when different components were made and when they were added to the galaxy and all those things. So I think we will learn quite a bit. Sorry,
yeah, JWST in particular is super exciting seeing that far back.
It's not just that, though. I mean, honestly, I think almost as interesting for galaxy evolutionary point of view is the MUSE instrument that you can point at a nearby galaxy and it can tell you what the age and the movement in the bar is versus the disk, and like that's a lot of new information that you can directly compare to the end products of your simulated galaxies, for example. So if the ages of bars, for example, like how long has that particular bar in that nearby galaxy been there? You can actually look at the age of its stellar component and go, well, the stars in it are this old. And you can actually see you can determine the pattern speed of the bar and determine the pattern speed of the spiral arms. So these are the things that we also sort of postulated so far, and now we actually have measurements on them. So that becomes suddenly like, yeah, a whole bunch of models fall out. So I think that's part of it. I think we'll end up understanding star formation on a statistical scale much better than we do now. Simply because we can start picking those things apart in nearby galaxies and on a grand scale. So it doesn't all depend on a single example anymore. So yeah, I think that's where all of this is going to up their game in every dimension, basically. So it should be very interesting.
Yeah, that sounds really interesting. Thank you. Side question, if you feel like answering it anyway, when do you expect your book to be available?
Well, it is at the printer. I have to give them a list of where I got the figures from. It should be available at the end of this year. U of L should purchase the license, meaning that you can just download the ebook from the library. And that's the way it works. This is it's sort of like a single purchase, and then everybody in the school ever can always download it. And I quite like that. So
yeah, that's really cool. You can have physical copies too?
probably 2.
Okay.
So yeah, I think they give you like 2 or 3 physical copies. I'm actually, having been the person that has lugged around the various Binney and Tremaines and all the other bricks of textbooks, I'm all for PDFs that I can search. Big fan, but yeah, I'll have a little book so that I can actually have a physical thing to show. But yeah, it looks like we're done. This was sort of my first pass at building a class based on the book. I've got some assignments that go with the book, so I think next summer I will redo this class, or the summer after that. But then I'll actually give the assignments so people can play with the kind of data that I was thinking about. Examples, like I don't have a ton of machine learning to go with it. It also becomes really obsolete very quickly. Machine learning is a very rapidly developing science, so this is the class that's going to date itself the quickest, I think. So we'll see.
Awesome, thank you.
All right, and then I'll see everybody after the break. Thanks for listening.
Good, thank you.
Have a good one.